Right.
Okay.
Okay, let me quickly just see what, sorry, I need to remember how to do this. Share my screen with you guys. Wait, I want to do this little thing, then share the screen.
Okay.
Yes.
So welcome to the session by Laurette Marais, and go ahead.
Okay. I'm not muted, am I? Hello?
No, I can hear you.
Okay, fantastic. Hello. Okay, so hi everyone. I'm Laurette Marais, and I will be talking about how GF has been used in a resource scarce environment to enable language and specifically speech applications. So this is the outline of my talk. I'll first talk a bit about what is meant by resource scarce, especially in South African context where I'm involved. And then I'll touch on why we use GF. Then I want to talk a bit about multilingual speech-to-speech application that we built using GF. It was already kind of busy being built at the Stellenbosch Summer School, so I can give an update on that. Then I will explain a bit the workflow that we followed so far when developing GF application grammars in this context, and I'll talk about where the resource scarcity is most felt. And then I'll try and describe how we've tried to get around that using some machine learning and specifically neural networks. And then I'll just conclude with some remarks. Okay, so in the NLP world, the term resource scarce is often discussed in terms of digital resources, but I want to start a bit earlier in the process, namely with human resources. So my opinion, and I know that it's shared by many of my colleagues, NLP colleagues in South Africa, is that our resource scarcity is really in skills. And of course, that starts with education. So I want to give a bit of a picture of how that looks. Unfortunately, South Africa's education is not in the best state. For example, in 2008, about 1.1, more than 1 million 6 or 7-year-olds started primary school. And 12 years later, only about 40% of them passed their senior certificate or matric exam. And passing here requires achieving 40% or more in a home language and 2 other subjects and 30% or more in 3 other subjects. So since we are mostly concerned with language and computation skills, I'll look at the results for those things. South Africa has 11 official languages, but the senior certificate exam can only be written in Afrikaans or English. So in principle, the first 3 years of school is taught in one of the 11 official languages, but even this is doesn't happen in all the schools. It really depends on where the school is and what the majority of speakers in the area are and so on. But then from grade 4, the official language of tuition is usually either English or Afrikaans, although by far the majority of learners are taught in English in South Africa. On the other hand, all the official languages can be taken as home language subjects, and these are then typically taught and written in the relevant language, and they can also be taken as first or second additional languages. So the specific subject taught in the specific subjects taught in any particular school depends on a number of factors, and this is mostly the availability of teachers. So this is not the case that in every school all these options are available. But be that as it may, about 33% of matriculants wrote and almost all of them passed, for example, the Zulu home language paper in 2020. Which is about 10% more than the expected number of matriculants. So Zulu speakers, home language speakers in South Africa, are about 22% of the population. But if you look at Ndebele, for example, which is another official language, only about half of the number of expected home language speakers of Ndebele wrote and passed the exam. Okay, but so still, if you consider how many kids started school 12 years before, only about 13% of learners achieved 40% or more in Zulu home language 12 years later, and none of them were taught in Zulu, the other subjects, beyond 3rd grade. So suffice to say that's not a large pool from which to extract budding Zulu linguists. And then mathematics is particularly problematic in South Africa. A recent international study found that by grade 5, almost 2/3 of learners can't do basic mathematics. And this is then borne out in the senior certificate exam numbers, which show that out of originally 1.1 million learners who started school in 2008, less than 31,000 passed mathematics with a mark that is high enough to be admitted to a STEM degree at university. So all this to say, finding students and engineers and researchers to work on things like grammar engineering is quite difficult. If we look more quickly at Zulu, it's the largest home language in South Africa, and it's understood by about half of South Africans, of which sadly I'm not yet one. Wikipedia is often used as a kind of useful indication. So it has less than 10,000 articles, and honestly, most of them are one sentence. I managed to click on the random article button long enough to find one that contained 4 sentences. And it has 28 active registered users. Typical parallel corpora that are used in machine learning is the Jehovah's Witness corpus and the Auchumatu corpus. People usually train their systems on the Jehovah's Witness corpus and get decent blur scores, and then they try it out on the Auchumatu corpus, and the blur scores reduce to, almost nothing. So that's what we have for training translation systems. And then in terms of other resources, I think the most relevant one is the XFST morphological analyzer, which was developed by my mother and colleague, the other Laurette, and her colleague, Zonia Bosch. And then, of course, the two of us are working on a Zulu resource grammar, but I'll say more about that tomorrow. So I work for the CSIR, South Africa's Council for Scientific and Industrial Research. And the voice applications we tend to target are high risk. Usually why that would be the case is because in a multilingual country, it seems to make sense to target those areas of miscommunication where it is high risk. And this is often correlates a bit with the literacy of the users that are targeted, because their proficiency in South Africans' proficiency in English is very often highly correlated with socioeconomic status. It often involves producer tasks. So if, for example, you have a doctor who wants to communicate with a patient, the doctor is much more like a producer of content than a consumer. And we can get away with limiting ourselves to a very specific domain because we kind of try to identify spots where there are real problems. But then obviously also, because of so many official languages and even more non-official languages or dialects, whatever, usually you need these applications to be multilingual, not just for specific language pairs. So the Awesomed application was a speech-to-speech translation application focused on the maternal health domain. And we can translate from English to Afrikaans, Xhosa, and Zulu. And the grammars together support about 4,000 utterances. There are 5 different multilingual grammars. They are kind of multimodal to make the speech work. And they're also supported by mini resource grammars for Zulu and Xhosa. Well, at that point, we've done some more work for Zulu. So the basic use case is that you have a doctor or a nurse who can speak English, and they want to speak to a patient who can't, and so they can say or input in a different way. I'll show soon how. So they say some utterance, and it gets recognized with the help also of the GF grammars. Then it gets translated and sent to the TTS in the target language. So like I said, maternal health, basically it's practiced at a few kinds of clinics and things in South Africa. And the one important mandate for these places are to provide respectful care. And so the communication gap often requires that patients need people to interpret for them, and this is often nursing staff, but it can also even be cleaners or security guards on the premises and so on. So you can imagine the kind of issue that has with patient confidentiality and just respectful care in general. So the app is set up in such a way so that the utterances supported basically only require a yes or a no from patients for the most part. So that's how communication is facilitated. Now let's see if this demo works. I tried to record something that captured my voice for the speech input, but I couldn't do it. So this is just the touch input. Right. So have I now moved on or have I not moved on? Okay. So I want to quickly talk about how the app kind of works. It's driven by grammar, obviously, and the user has two input options. They can either say the utterance that they intend to be translated, but if they don't know the utterances that well, they can also use screen input. So this screen here shows the user in the process of selecting the sentence. Did the pain start about 2 hours ago? So they can make selections from those drop-down boxes. And the grammar supports the screen, or at least the screen is driven by a grammar that's marked up with important information about, so which parts of the screen should go where. So the static pieces of the text need to make sense, although at least whenever a selection is made, the entire sentence has to be nice and grammatical. So for instance, as soon as the patient, or as soon as the doctor or nurse selects, changes the 1 to a 2, you want all the strings in the drop-down box relating to time measure to change as well. So you want, instead of hour and day and so on, you want hours and days. And also the static pieces, if you change the time indication of the sentence, you want the tense in the verb to change, etc. So that's all done by a version of the English grammar. And then there's a lowercase version of the same grammar that is used to interface with the speech recognition. So we actually exported that as a JSGF, and it serves as a language model for this recognition. And then at the end, of course, in the target language, we want some capitalization and punctuation, so that serves as some information for the text-to-speech component. So if there's time at the end, maybe I can talk a bit more about this kind of interface. But anyways, for now, I think that's enough. So I spoke about different versions. So we basically used incomplete modules to have the different versions of the English grammar. But for the target languages, obviously, it doesn't really matter that you only need the one version. And I want to quickly say something about the two Nguni application grammars and how they basically work. So the semantic tree in the top right is very simple. It basically expresses the question, have you experienced bleeding recently? If you change the symptom in the tree, the English sentence, so for instance, you have severe headaches, or what's my example? Yeah, severe headaches, yeah. So typically in English, you only change the noun phrase and it still makes sense. And honestly, we did develop the English to be kind of formulaic in an attempt to help users to learn the utterances supported by the grammar. So obviously you could also say, have you been bleeding recently, or yeah, anyways, the English was developed with this kind of formulaic thing in mind. But for the Zulu, you can't do the same thing. If you change the symptom, then you basically literally change the question from maybe you sometimes with bleeding recently to maybe sometimes you were bothered by a head that is painful recently. So yeah, we can see how that change is affected if you look at the abstract syntax tree from the resource grammar. So besides the noun phrase that changes, which is the orange text up top, you also have a copulative predicate that is now replaced by a passive verb predicate. And this is not an isolated example. This was a relatively pervasive feature of developing these resource grammars. It wasn't, unfortunately, as simple as changing lexical items and even small chunks. It usually involved the whole predicate changing. Anyways, the app was piloted at 5 sites in various parts of the country. And unfortunately, the pilots themselves and our entire evaluation plan was disrupted by the pandemic last year. So the feedback that we had hoped for has fallen far short. So we have some feedback. It's relatively superficial, but it was mostly positive. And it seems to have achieved at least our goal of assisting to enable respectful care. I think, honestly, at this point, people were happy to just have something that indicated to the patient that an attempt is being made to communicate with them in their own language. And the fact that we could provide good translations meant that whatever was said was at least understandable. But we also, so the pandemic hit, and then we also decided to, we were basically in the last throes of development when all the lockdowns around the world were starting to happen. And on the spur of the moment, not knowing anything about this virus and how it's going to behave, we tried to be useful, and we decided we could perhaps adapt it to COVID-19. So in the same way as during the development of the maternal health application grammars, I spent some time consulting with nurses and doctors about what content should be covered in an app like this. So we adapted some of the abstract grammars. We changed the more obstetric and gynecological grammar. We exchanged that for a COVID specific grammar, but for the rest, a lot of the grammars could stay the same. Although we had to simplify them somewhat, because what seemed to be very necessary at the time was to have it available in all 11 official languages. And we just didn't have the time to basically bootstrap resource grammars. We had to bootstrap application grammars. So we made some simplifications. And actually, I think this version is still up on the Play Store. So I'm sure if you search for Wezamed, you would be able to download and test it out. I hope it's working in good order. Okay, so that's the app that we were working on, and that kind of segs into the workflow that we followed. So at the very start, we wanted to develop mini resource grammars in parallel. So we kind of developed the following workflow. And when I say we, I mostly mean I. So the first step was to develop an abstract application grammar in consultation with language practitioners, not language practitioners, healthcare practitioners, and so on. And then it was relatively quick and painless to develop English and Afrikaans concrete grammars. But then I don't know Zulu or Xhosa. So we created a kind of a representative corpus of English sentences. And basically what that means is you choose your basic template sentences, and then you swap in the different concepts to see how they would influence your sentences in the grammar. And then we obtain translations for these we obtained translations. And then it was, so since we didn't have resource grammars at all at the time, it was kind of a parallel process of manually analyzing the translations with the help of expert linguistic input. And then we would implement the mini resource grammar so that we could implement the application grammars. And there were a few iterations of some of these steps. The representative corpus was fine, but obtaining translations had to go through a few iterations, because you would maybe the original translation contained some slightly obscure construction that didn't apply as generally as we had thought in the beginning. And I have to say, it also became increasingly clear that mother tongue input was limited in its usefulness. The progress sped up quite a bit when I approached the Zulu lecturer at the University of Pretoria for help in translating and analyzing the representative sentences. In fact, it's no exaggeration really to say that the professional language practitioners that we consulted initially had basically no formal knowledge of the morphology and syntax of the languages. I'm not even always sure they understood the concept of morpheme, and they understood how the agreement worked, but they couldn't put a name to it or really answer some of my more technical questions. So that was good to learn. And then for the COVID app, we kind of had a slightly different approach. We couldn't use the mini resource grammars because we wanted to bootstrap to application grammars. We couldn't bootstrap mini resource grammar. So, but we still did use the Zulu resource grammar specifically, because the workflow was to also create this representative corpus, and then we get translations for all the languages, and then we only analyze the Zulu ones to kind of figure out what the moving parts need to be. So we used the resource grammar in that step, and then we implemented the Zulu, and then from the Zulu we could kind of massage bootstrap and then massage them so that they fit the translations that we ended up with. And I think that worked relatively well. It wasn't such an iterative process, but in principle, we actually did have to go back for some of the Sotho languages to get some more translations, because we realized that what we knew about Zulu made us make some assumptions, and in Tswana, I think it was Tswana or Sepedi, maybe both, we had to get more translations to figure out some differences that occurred there. And then obviously evaluation step is usually just to generate some random translations and have them checked. At this point, that's what we're doing. So this kind of turned into a more general workflow for when you have a resource grammar, but you don't know the language. So you develop the abstract and the English, you get this representative corpus of sentences, and then you use the resource grammar to analyze your translations, and then you figure out how to use the resource grammar to implement the concrete grammar. So it's basically you essentially obtain a mapping between the abstract grammar syntax and the resource grammar. And so obviously that is it's at exactly that point where the bottleneck occurs. It's not only does it take quite a while to figure out what's going on in a specific domain grammar, but it also uses a very specific set of skills, and not one that is in oversupply in our context. So you need obviously to be able to engineer grammars, and then you need some familiarity on a formal level of Zulu morphology and syntax. But what we did notice was that that step kind of produced a parallel corpus of semantic and syntactic trees, which could be obviously extended with linearizations as well. So we thought maybe we can use that in a different way. And the idea was to basically see if this mapping that you have to develop when you build a domain-specific application grammar, whether you could kind of learn that. It's something maybe that a computer can learn. And for this work, obviously, the data required could perhaps be created or augmented from this small seed corpus. So we tried this in the parsing direction first. So the two main reasons for that, I guess, is that you go from a more complicated tree to a simpler tree. So that seems to be the easier route, easier to learn. And then also the benefit is that hopefully, so neural nets tend to be obviously more robust than rule-based systems generally. So, and that's also the direction for which it's most useful to have some robustness in terms of input. So that's why we went for that direction. And the basic idea of augmentation was to have this idea of a rule that captured the intuition that if you have a semantic tree and a syntax tree, and you know they fit with each other, and you also know that a change in the one necessitates a specific change in the other, then you can make new trees. So from this little corpus, the seed corpus, you can basically try and figure out if you change in the semantic, if you make a change in the semantic tree, what does it mean for the syntax tree, and can you then basically blow that up using the generation capabilities of the grammar, of the GF runtime, I should say. So we had to pivot a little bit. It was partly strategy. Actually, our main motivation was to counter a perception in our immediate environment that GF was only to be used for translation. Like, that's what it could do. So we set up a proof of concept question answering system that used a grammar that I would say was not drastically smaller than any of the Aweza-made grammars. What it did cover in more detail was numbers between actually up to 99. And this is relatively significant because in the Bantu languages, numbers are not a coherent morphosyntactic category, but they are expressed using quantitative pronouns, adjectives, nouns, and modification of adjectives and nouns using adjectives and nouns. So that it was kind of in one sense, we added some linguistic complexity, maybe. And then the question, the natural language understanding part. So question understanding is useful as a use case because you only need to understand, and the verifying of what you did is kind of in the answer, or you can build it so that the answer validates or verifies what the user expressed. So for the Aweza-made application, the fact that the screen updates with what was understood. So even if you use the voice input, the screen updates with the little utterance so it's still powered by the grammar. So it kind of serves as a verification for the user of what they are about to translate. So anyways, the question answering kind of solved that little problem. And the system that we used had this more or less this architecture. There's a weather fact grammar that sits in the middle, and each language is supported by a pair of concrete syntaxes. One for expressing questions about weather facts and one for expressing answers. So and then there's the weather QA module that uses this grammar, as well as a web service that obtains up-to-date weather information. The Open Weather Map one call API is what we used. So it provides current weather data as well as historic data for 5 days. And then up to the minute forecasts for the next 60 minutes, hourly forecasts for 48 hours, and daily forecast for 7 days. And this weather fact grammar supports basically questions about these kinds of weather conditions for 41 of the major locations in South Africa. Capital cities, large cities, places with airports, etc. And how the question answering works is that it basically comes down to completing abstract trees. So in the question asking concrete syntax, you kind of underspecify the linearization so that what the parser produces a meta variable in exactly the spot where you would expect the answer to be. And then this tree tells the question answering engine which information to request from the weather service, and then it can construct that missing subtree, completes the tree, and then this complete tree is linearized as an answer. So for example, I'm not going to sport with your intelligence by reading the Zulu, but basically it's how much will the wind blow in Cape Town in 2 days. And because we haven't said anything about the wind speed as such, it pauses with a question mark under the wind speed. And then the question answering system can know what to look for and what kind of tree to construct. And then the answer is linearized as the wind speed in Cape Town in 2 days will be 14.5 kilometers an hour. At one point, I did contribute something to the GF Contrib GitHub with a README that says a little bit more about this, if anyone's interested in looking at that. So, okay, we want to simulate a concrete syntax for questions using a neural network. So this is the workflow that we basically ended up following. Still an abstract application grammar with an English concrete syntax. We still create a representative seed corpus of the English sentences, and we obtain, in this case, we obtain 2 sets of Zulu translations, just because we were trying to figure out, so obviously you want more flexibility and robustness with regards to user input, so we went for 2 sets of translations, as we didn't have to actually manually implement 2 different concrete syntaxes or introduce variants or any of that. So like I said, the representative corpus was constructed basically having these template sentences and varying them, varying all the categories so that you can figure out the effects they have in isolation. And if you know enough about Zulu, you can kind of start imagining what you should ask and what you shouldn't ask. The one thing we didn't elicit explicitly from the seed corpus is how the number system works, because that the rules for that was relatively easy to write by hand, because we know how the number system is, although it's not one coherent morphosyntactic category, it does behave itself relatively well, so we know how to do that. Okay, so then we obtain parse trees of all the, then the idea is to obtain parse trees of all the translations, and then you apply these augmentation rules to get many more semantic syntax linearization triples. Okay, so then you need to evaluate the data. At this point, it would become clear if your choice of seed corpus was sufficient, because the errors would pop up. In the case of the weather grammar, the only errors that we found was the incorrect use of the immediate, future, and past tenses, where the remote tenses should have been used. So for example, because the grammar allows all numbers up to 99, you can say things like, what will the weather in Johannesburg be in 78 days? And so for this, you would typically need the remote future. But since the Open Weather Map service only gives data for 7 days, we decided not to fix this. But the point is, we could have basically fixed this if necessary. So we would have elicited more translations to make sure that we would just have started the process slightly from the start with new translations. Okay, so and then once you have the syntax trees, you linearize them, then you have these nice triples, and then you are ready to train neural networks. I have to say something about how the data was prepared. So the seed corpus 2 sets of translations gave us 152 translations, and we extended the Zulu resource grammar to be able to parse 148 of them, and that included at least 1 translation per English sentence originally. Hopefully, as the resource grammar becomes more complete, this it wouldn't be necessary to extend specifically with necessary constructions and so on. And then we actually managed to create over 300,000 triples using the data augmentation rules. And we made sure we checked against all the possible trees in the application grammar to figure out if we had missed any of those. And we did miss a few, but those were only the ones where there was a leading 0 in the number. So that wouldn't have made any difference, I think, from a user perspective. So we just ignored that. And then, so because some utterances contain these numbers up to 99, these kinds of utterances were disproportionately represented in the augmented data. So we did a bit of a heresy, machine learning heresy. So we duplicated some of the data, and we used the tree size as a proxy to determine which ones to duplicate. The other option would have been to throw data out in an attempt to balance, but we weren't really interested in building a neural network that would generalize beautifully. In fact, we would have basically done our job if all the sentences that would have gone into a concrete syntax could be handled by the model. So we went for duplication instead. Okay, the next step was to think about how the inputs and outputs of the neural nets would look. We wanted to try and exploit the new transformer architecture. So we set up the problem as a sequence to sequence one. So for the input, we had a few options. Zulu is notoriously difficult for machine learning problems because of the fact that it's morphologically complex, and it's also conjunctively written, which I think is kind of standard for morphologically complex languages, but some of the other Bantu languages have disjunctive orthography. So anyways, we had a few options. We could just use word boundaries as is. We did a syllable boundary. We've tokenized on syllable boundaries. And in Zulu, this is actually relatively easy because syllables are almost all open. So it was easy to write a little script that does a decent job. And then we also, just for the heck of it, tried tokenizing at the character level, see how that worked. Other option was to use a syntax tree string as is, or maybe even just with the parentheses removed. And then the other idea was to try and just extract all the lexical functions from the syntax tree and use that as a sequence for input. So the last two options obviously introduce the GF runtime at this point. And so if parsing for some reason would fail on user input, you would have failure here. So there is the idea that maybe using the linearization to train is a bit better, because as long as you end up, as long as maybe the speech recognition part produces a Zulu sentence, you can still use your model. And then for output, we could use a semantic tree as is. But we kind of did the same thing as for the lemma sequence. We produced a keyword sequence. So this meant that we did not expect to obtain fully formed trees from the neural network. But it's relatively trivial to write a concrete syntax that can parse these keyword sequences back into trees. And in a way, it seemed like the safer route anyway, because sequence to sequence networks are not good at inserting balanced parentheses in sequences. They might be better at producing keywords where the keywords themselves can be somehow traced back to the input tokens. So we went for the keyword sequence one, and this also meant that we had to adjust our architecture a little bit. So instead of a Zulu question concrete syntax, we have this keyword concrete syntax that is easily built. Basically, it parses these keyword sequences that are made up of function names in the abstract syntax into trees. But then the advantage is that you could, in principle, build models for any language that produces these keyword sequences. So it's not language specific in that sense. Okay, we wanted to evaluate in some way. So we could just evaluate in the obvious way by splitting our augmented data into training, validation, test sets, and then test against the test set. And testing in this way, given that we evaluated our augmented data, and the augmented data basically represents everything that we would want to be able to handle, this test would basically tell us whether we have successfully developed a model that can understand questions in the same way a concrete syntax would have understood them. But we could also go one step further, because one possible advantage of using neural networks is improved robustness. So we wanted to see if we can do better on other kinds of input that we might want to be able to handle. So variants that we might not have considered putting in a concrete syntax. So we prepared new independent, well, we basically obtained new independent sets of translations from entirely new translators. And in fact, I have to say that there was only about a 13% overlap in the sentences they produced for us. So it seems to indicate that it's quite important to have this robustness. Anyways, so But the seed corpus itself was not built as an evaluation corpus. In fact, it is very repetitive and biased almost by design. So in order to have a more balanced evaluation set, we tried to augment it in a similar way. In this round, we didn't extend the resource grammar with any new constructions, so we ended up with only 71 parsers. But we did manage to blow that up into almost 140,000 utterances, and then we just selected 100 of them at random. And so this formed our additional evaluation set. And here are some of the results. So the F-score, you probably know, it's the measure that balances precision and recall, and we just used, I think, the NLTK function default parameters to compute that. And then we also have this P-score, which is the percentage of perfect predictions achieved by the model. And so this would typically be an indication of how many times the model produced exactly the right keyword sequence, as in that's what the concrete syntax would have helped you do. And also this would be all the cases in which a user would not need to re-engage on that specific question. So it was perfectly understood. And then, so the blue indicates the scores achieved on the unoriginal, or the original augmented data test set. So basically that's, those scores answer the question of whether the model was able to simulate a concrete syntax in the parsing direction. And then the green scores indicate the model's achievements on the independently translated and augmented data. So I think what is relatively interesting here is that almost all the models could basically replace a concrete syntax in this very specific, for this very specific use. I have to say that the lemma to key star that we did was just to kind of show that, so that was done on the original seed data, just to show that if you have the seed corpus, you get nowhere. You really do need to augment, and for that you need a resource grammar. The model that generalized best to the unseen input was the lemma to key model, although it performed almost exactly as well as the syllable to key. So that's where you give a linear Zulu string and you just tokenize on the syllable boundary. And what is also interesting to me is that the token to key model performed by far the worst. And this basically seems to indicate that as long as you break up the Zulu tokens in any systematic way, you get a win, and a significant one at that. And so the syllable to key had the best P score, but also within the range of the others. So yeah, basically that's that was encouraging, because what we achieved now is a workflow that does not rely on grammar engineering skills at all. At most, you need to be able to use the resource grammar to parse your sentences. That's obviously if the resource grammar is complete enough to deal with the input. If it's not, then you need some grammar engineering, but that's on the resource grammar level, not on the application grammar level. And as long as someone can then use the resource grammar, they can augment the data for this very custom use case. And skills for machine learning are obviously much more prevalent and common, even in South Africa. So hopefully this kind of thing could, it's a workflow that's more widely, could be more widely used, hopefully. But you still end up with a lot of the advantages of an application grammar. So to conclude, GF is a good fit for speech and language applications where there's resource scarcity. In South Africa, the resource scarcity starts with human resources and basically goes on from there. And then you could, if you have a resource grammar, it's possible to leverage that to generate enough custom data to train models that perform similar to application grammar concrete syntaxes. It's less flexible in some ways. So obviously this is just in the kind of the parsing direction. So you wouldn't be able to drive a dynamic screen as in the Awesomed application using this approach. But on the other hand, from a voice interface perspective, you do get a bit more flexibility with regards to user input. So what you lose on the one hand, you kind of make up for in a different way. Yeah, that is, I see there are some questions in the chat. Thank you very much for listening. Let me quickly see, generally, test question answering systems have the ability to answer what to who, questions around how or when. Oh, yes, how or when is much more difficult. We haven't actually looked at this in much detail.
You want to read out the question, so if people are watching this from video, so, yeah.
Yeah, okay. So the question is, I generally test question answering systems. I always find that these knowledge-based systems have the ability to answer what or who questions rather than how or when questions. How do we solve this matter? The short answer is that we haven't yet. And what is the advantage of GF over other methods such as tree bank? I'm not sure if you mean tree bank as in just generally tree banks, or if tree bank is some kind of framework that I'm not aware of. If it's tree banks, generally speaking, it's just that there aren't any. There's no Zulu tree bank. The closest we have is a morphologically annotated corpus, but I actually haven't looked at the quality of that yet, so I can't say. Okay, so are there any other questions?
Would you say that you're happy with your experiments with neural nets? Like, do you see you want to continue that if you want to bootstrap, like develop other languages of South Africa, or would you prefer another approach?
I think it's promising, especially when you want to develop products that solve real problems. So I was pleasantly surprised. I used a more traditional sequence-to-sequence architecture at first, and it wasn't that great. It only achieved about a 60% success rate for the not even for the. I think the F scores were relatively low. And so I wasn't very encouraged by that, but then I decided I should probably try the transformer, and it made a big difference. So that was interesting to see. And I think what this helps with is exactly just it's a very specific use case, but if you want to be able to parse, develop these, so you still have a lot of what GF allows. You just basically replace the runtime. How the runtime is used. I think it could be useful. I would like to look at language generation next. Yeah, I don't know. We'll see.
Okay, thanks. Krasimir, Arne, Michal.
Okay.
So when we did a similar application for doctor-patient communication in digital grammars, my impression is that when you go to the customer or the potential buyer, the first reaction is that they take the phone, they say something, and they get disappointed because they don't get answer or they don't get translation. And of course, the reason that what they have said is actually not in the application grammar. Also, the idea of scrolling through menus and searching for the right phrase didn't look very appealing to them either. I wonder whether you got the same experience, or maybe the problem was smoothed out by using the neural networks.
Yes, so definitely the speech recognition is somehow a very high risk input type. People lose their confidence very easily. That's why we developed this dynamic screen thing as a kind of backup, so that people felt that even if they said something that wasn't understood, it could be for various reasons. It could either be something that is not modeled at all and the meaning isn't captured in the application grammar, or it could be that they just said it a bit wrong. And I think the second one is more discouraging because they probably have this idea that I've said this sentence before and then they can't recall the exact wording and now it's not working. So that's why we had this dynamic screen where they could make selections so that even if the speech recognition fails, they kind of still feel that they can maybe navigate. And the dynamic screen was a way of, so at first, we used lists that expand as you make selections, and that I think that was very cumbersome. So the screen that updates more dynamically and you have fewer kind of template sentences that serve as your as the starting point, I think is a bit more user friendly. But that's part of what I was a bit frustrated with, that we couldn't test very rigorously with users, is to see if this does actually work better. And obviously, this kind of interface it does limit the application grammar in a way, because I wasn't able to find something that I'm happy with for adding to the kind of extending the tree. Basically, what this interface allows is you have a tree and you can swap in the nodes themselves, but you can't add subtrees that are more complicated, at least on the abstract grammar level. So there's still some user experience work left to figure out if this is a useful interface or not.
Okay.
Thanks. Arne?
Yeah, thanks, Laurette. Very impressive work. And also, we have had some experiments and training transformer from linearized trees and their linearizations. I think the results have not been nearly as good as yours, but maybe it's because we have tried it on the full resource grammar and not the small grammar. So do you think the size of the grammar is, or is it the depth of the complexity of the sentences?
I'm not sure.
Yeah, different.
Yes, so I also have ambitions to try this on more complicated grammars. I think maybe a bit encouraging here is that the Zulu has a lot of the application grammars were actually very heavy because of the level, if you have the syntax tree, the change that you have to make to implement or to realize differences in the abstract syntax tree go up all the way to the verb phrase level. So even if the application grammar abstract syntax is not that complicated, the diversity in the Zulu syntax trees was relatively high. So I don't know if that is an indication of the complexity. So I have this hasn't been discouraging in that sense, and I think based on the fact that the Zulu was relatively linguistically diverse, I think maybe it could work if you make the grammar more complicated. But honestly, I still have to try that. So
thanks. Okay. Is your software owned by the organization, or have you released, or could you release some of it?
We haven't released. So are you talking about the mobile application?
No, I'm actually thinking about this. So if you want to build the same pipeline for the neural training, for instance, if there is something in your software that is there's certainly something that is very clever, and that's right way. It's tested all the combinations, so that's also, if it is possible to share. So
yes, so I think we have some responsibilities to for the next year and a half with regards to a project, but we're trying to, I don't know if we've been brave enough to look at the Zulu resource grammar code, but that is more or less, we try to keep that up to date, and it's not very up to date at the moment. So at least in terms of, obviously the resource grammar is up to date, and I think we could relatively easily release the application grammar, but for the augmentation, I think it's not at this stage. It's a bit sensitive, but hopefully, the idea is to share as much as possible of this, because obviously we want it to be useful to people building applications and also using GF So unfortunately not at the moment, but I think maybe a year and a half, hopefully.
Okay, so there is nothing that prevents it in principle.
No, I don't think so. No. Yeah.
Michal next.
Hi, I wanted to say something similar to what Krasimir said, really, that it's a shame or it's a pity that you didn't have a chance to do more testing or more kind of user acceptance testing, because it's an interesting question how people respond to this kind of user interface where you have this, as you say, the dynamic screen where you have these sentence templates, and then some of the words are clickable or tappable, and you can click or tap on them and then select something else. And then the sentence kind of updates and you get a translation. I mean, it's a clever idea, but it's not clear yet how well or not well users respond to that. I mean, obviously, yeah. I mean, so Krasimir said that in Sweden, they often see this response that people kind of come up with a sentence that they have in mind and they want to translate it. And the app doesn't do that because it doesn't have that particular sentence. Right, and but then again, I suppose if you're doing a translation in a language pair like, I don't know, Swedish and Polish, which is already relatively well populated by existing tools, there is machine translation already available and things like that. So the potential users have something to compare with. So their response might be like, oh, this isn't as good as Google. But then if you have a language pair like English and Zulu, where probably there isn't any existing statistical machine translation, or maybe there is some, but it probably isn't as good as in mainstream global languages. So there the response to a tool like that might be more positive, because then people might say, well, okay, it doesn't have great coverage, but at least we have this, because otherwise we have nothing. So, but this is all speculation, right? It would be really, really interesting to know to sort of have some data, have some observations about how actual normal people out there respond to this kind of user interface. Yeah. I know you agree with me. It's a shame that we don't have any more kind of data about this. Yeah. On Wednesday, I will be showing something similar, a similar kind of a user interface with sentence templates and clickable things. So
I look forward to that very much.
Okay, thanks very much.
Pleasure.
Yes. So I have just a little comment to actually Krasimir and Michal. So the most successful, even commercially, application for healthcare translation in Sweden is Care to Translate, which is an app that is basically just a list of phrases, nothing else. And then you have a search function, so you can search for a keyword that matches in the list of phrases. And this has been enormously popular, and they are raising new funding and whatever. So. But it has over 40 languages, so that's one of the strengths. But it's mainly used by Swedish professionals when they talk to their patients.
I want to say that when we started out with this, that is exactly what the developer and some of the other team members had in mind, and I think I think the strength of that is that users know what to expect. And obviously, hopefully, with the grammar, you kind of always feel like you can do better than that. But then managing the expectations of the user, I think, becomes more difficult. As I find people don't have a very good sense of what's in between. I can say these 10 sentences and I can say absolutely anything. So helping people understand that there might be something in the middle. I don't know, that was difficult for us.
Yeah, Krasimir.
I just wanted to say that the strength of solutions like Care to Translate is that you can actually do search, not parsing. So you can just say a word which is in the middle of some sentence and you still find it. And this is more difficult to do with the grammar. I did some experiments, but you get exponential complexity if you do it like this with the grammar.
Yeah, so what you can do is that you can actually use a grammar to augment a set of phrases. That's and then use that technology. So there are many We did that in one of the experiments also.
Yeah, that's another solution.
Yeah.
But neither of them gives you the full set of variations in the grammar. But it gives you something else on the other hand.
Yeah, just raising a point from the chat. There was a question if, or like more like a suggestion to check out Mazzacane. Maybe this actually is a better comment for tomorrow's talk, but maybe that's just you can comment briefly, like if you're familiar.
I didn't read the comment. Is it just to have a look at what they're doing?
Yeah, I don't know. I mean, like, would you who said the comment? Did you want to say something about it? Like,
honestly, I haven't looked at a lot of what they have done. I've, if I have to be honest, the people training on the Jehovah's Witness corpus and then testing on the other corpus, some of their participants have exactly that route. So I know, what I do know of what they are doing is they are trying to crowdsource more data. And I think we are, in a sense, working on the same thing in different ways. So they are trying to get the data from somewhere. I'm not sure what the expectations are, because honestly, the data isn't out there to be found. It has to be created. And I don't know exactly to what extent their efforts are about creating data, translating, for instance, Wikipedia, or contributing sentences, or what model they want to follow. So this is a bit of a different approach to creating the data that you need. So I'm aware of their stuff. I think they come from a more typically neural machine translation kind of angle, and we might arrive at different kinds of solutions, hopefully working towards the same thing.
Yeah. Has there been any like suggestions to, like, you know, use GF grammars for data augmentation, like?
Well, so this is the first effort that I know of. I think there are 2 people working in South Africa on application grammars, and I think it's me and Winston. So it's not like it's a big community and someone has said this already. This is actually exactly an attempt to use GF and maybe find some common ground with people working on different kinds of solutions.
Yeah, thanks. Any other questions, anyone? Oh, so okay, thanks for your talk, and we're going for 1 hour 40 minutes break now. So see you at 8 p.m. Singapore time, and we can keep the Zoom open. Like, I'm gonna basically go home from the university, but I can make someone else a host. So you can hang out here, or you can just, you know, quit and come back.